Okay, guys, we're on to 6.2 telescopes, the giant eyes. Okay, so let's go into this. Okay, so there's two important parts about a telescope. You must know them both, okay? Number one is the light collecting area. The second is angular resolution, okay? So let's go into those two. So light collecting area, angular resolution. First one, light collecting area. Okay, light collecting area is pretty easy. I mean, a telescope is just that big tube, and at the back, most modern ones are like this, they have a big mirror. The bigger the mirror, the better the light collecting area. So basically, the larger the telescope, the better it's going to work. I'm not talking about large in terms of length, I'm talking about large in terms of width, okay? Because that's the mirror that's collecting light at the back. So a telescope's diameter tells you how big the light collecting area is, okay? And to find the area, I mean, you guys took geometry already. It's simple. It's pi r squared. That's the area of a circle. The telescope at the bottom of the telescope is a large circular mirror. And to find the area of that mirror is pi r squared. Okay, the largest current telescope, you need to know this, is about 10 meters long. Okay, it's about 10 meters in diameter. Okay, if you want to get an idea of that, that's about 30 feet. Okay, so if you think about the portables in our classroom, it would be about the diameter of the mirror on the bottom of the telescope would be about as long as the portable is, the long width of the portable. Okay, that's how big these telescopes have gotten. They're huge, okay? And the second largest telescope in the world is about 2 hours away from here in Fort Davis, okay? It's called not Sunspot, I'm forgetting the name right now. But it's in Fort Davis. It's a pretty easy drive. You can do a tour over it. You can go up there and look at the telescope. It's gigantic. Okay, you're going to need to be able to do this math. So look at it. Watch me do it. It's not difficult. We are using the pi r squared formula. So how does the collecting area of a 10-meter telescope, so the largest in the world, compare with that of a 2-meter telescope? Okay, now some people are just going to automatically look at it and be like, well, it's 5 times bigger, therefore it must be 5 times better. But no, remember, it's a circle. It's a circle. I'm going to take out a pen and I'm going to write something real quick, okay? So look at this. Our formula for area is pi r squared, right? Pi r squared, that is a 2. So what you want to do is you want to find the area of both of these. So you got pi. One of them has a diameter of 2. So that means it has a radius of 1, correct? So it's going to be 1 squared. 1 squared is 1. So that means the area of this telescope, the 2-meter one, is only pi. The area of this one is just pi. Okay, let's find the area of this one, the 10-meter one. Okay, so it's going to be area equals pi. Okay, r squared, what's the radius of a 10-meter diameter? It's divided by 2, right? So it'd be 5 squared, and that is a parentheses. It's not coming out very nice, okay? So that would be 25. 5 squared is 25 pi. Okay, and my pen's not working very fast. Okay, 25 pi. Okay, so the area of the small one is pi. The area of the large one is 25 pi. That means that is 25 times greater than the smaller one. Okay, so it is 5 times bigger and 25 times better at seeing light. Okay, the light collecting area. Okay, so these things are, the bigger you make it, the much better it is. Okay, so let's keep going. Okay, number 2. So the first one was the first one was the light collecting area, basically the size. Okay, number 2 is the angular resolution. Okay, so I don't know if you guys have ever. Let me explain what angular resolution is first. Okay, so if you guys have ever seen like a car traveling towards you from very far away with its lights on, when it's really, really far away, it kind of looks like a motorcycle. It's just one light. Yeah? But as it gets closer and closer, that one light begins to define itself more, and you can start seeing both lights. And you can be like, oh, that is a car, not a motorcycle. Well, the same thing happens with angular resolution, okay? So the nearest star to us is, now let's just do this. All the stars that you guys look out at night, about half of them are binary star systems, which means there's really 2 or even more stars that are a part of that system. But you guys, and me included, are seeing them as one star. And the nearest one to us, Proxima Centauri, it's a 3-star system, and we thought it was 1 star for years and years and years because we didn't have telescopes good enough to distinguish between it being 2 stars, so it appeared to us as 1 star. It's the same idea as this car. When it's far away, you see both headlights as 1 headlight. Okay, and this is called angular resolution, and it has to do with the type of light that's coming at you. So if it's radio waves, if it's microwaves, if it's visible light like the stars, if it's gamma rays, all of them have different distances that you can distinguish between 2 lights versus 1 light. And basically, the size of the telescope will determine when you can distinguish between them. Okay, so but it will be different depending on what type of light it is. So we don't stick this in with the light collecting area as just being size, because the size would matter depending upon what type of light is entering it. Okay, so this is angular resolution, the ability to distinguish between 2 different light sources instead of just seeing it as 1 light source. Okay, that's angular resolution, and we just spoke about that. Okay, what are 2 basic designs of a telescope? Okay, so you got 2 types of telescopes, okay? They're pretty easy. You got a refracting one and you got a reflecting one. Okay, I just spoke to you guys about a reflecting one. Okay, I'm going to show pictures of both of these. Now, refracting we just spoke about in 6.1, that's when you use lenses. Okay, that's going to be those old school telescopes like this, where you have lenses on both sides and you look through the end of it. Okay, that's a refracting telescope. Not many people use these anymore, okay? Because you got to have 2 lenses, okay? And now, look at this gigantic refracting telescope. This is the largest one in the world. The lens that you would have to have on that thing looks like it'd be almost about 4, maybe 5 feet in diameter. That's very expensive to make a piece of glass that big that is so detailed that it's going to refract the light to a certain point on the other side. Okay, so we just don't want to make big telescopes like this because it's going to be very expensive, and these lenses are going to be extremely heavy and just extremely expensive. So we don't really make a whole lot of refracting telescopes in terms of the large ones. You can still buy them if you go out to the store. You can buy a refracting telescope, but it's much better to buy a reflecting telescope. A reflecting telescope just has a mirror at the bottom, okay? And then it reflects it. There's a lot of different ways you can reflect it. You can look at it from the bottom. You can look at it from the sides. These are the 3 types of reflecting telescopes. The ones that are most used are the Newtonian focused telescopes. And it just comes down here to the bottom. It reflects it up to the front. And then you can look at it from a little lens here at this point right here. And these reflecting telescopes are very cheap to build compared to the refracting ones, because you don't need, I know you guys are thinking like there's a mirror down here and you're thinking like a mirror you might have in a bathroom or something. You could totally do that, but all they do is they grab these like big hexagon shaped things a lot of times, or they can even just get a piece of a thing. Now notice how they're kind of curved. So you need to have some curved surface, and as long as you spray or put something on top that will reflect light, you're good. So it doesn't have to be like a mirror from a bathroom or something. It doesn't have to be that perfectly reflective. But you can do something like that, but that would be more expensive. So that's why these things are cheaper to build, because you don't have to buy this gigantic lens that has to be perfect, okay? So that's why we build a reflecting telescope. So the largest telescopes in the world are going to be reflecting telescopes. You're not going to see refracting telescopes. So that 10-meter diameter one, the largest one in the world, I believe it's in the Canary Islands, it is going to be reflecting, okay? Okay, here's some telescopes. These are the ones on top of Hawaii, and they're the Keck telescopes. They're really cool. I think I have some pictures of them later on. Okay, but what do telescopes do? What do astronomers use them for? So there's 3 reasons, okay? These are the 3 right here. Imaging, spectroscopy, and time monitoring, okay? So, let's just go forward. Imaging, they're taking pictures, okay? Now, guys, no picture you're going to see from astronomy telescope is going to be like, oh, I snapped a shot and this is it. What they do is they snap a shot, they can do multiple photographs, like I said in 6.1, and they also do them in different colored lights, okay? So they'll tell the telescope to focus only on red light on a certain time, and then on this one only on green light, and then on this one only on blue light. And what they'll do is they'll put them, overlay them all to get one colored image, okay? So they are combining images to do this. And guys, sometimes you see images in like X-rays. They might put an image in X-ray. Guys, we cannot see X-rays with our eyes. Okay, so they are not showing you an X-ray image. What they're doing is they're taking X-rays and they're switching it to be visible light. So they put it into the visible light portion so we can see it. And then that's like their own idea of what it would look like if it was invisible light. I mean, that's not exactly what it looks like. It's like an artistic rendition of what that would look like if it was visible light, okay? So, imaging. And here's what I was just saying. Color is sometimes used to represent different energies of non-visible light. So, like this is a picture in X-rays. Perfect. So we got the green X-rays, red X-rays, and blue X-rays here. They are using green, blue, and red, the visible light colors, to show you what they think this X-ray ball thing would look like, okay? It's not an actual picture in X-ray that you are looking at in X-ray, okay? So let's go forward. Okay, so I just showed you imaging. Number 2 is spectroscopy. Okay, so what that is it's the breaking up of light. Kind of like how I said we use a blue, green, and red filter, and then they'll overlay them. This is what that does, is it breaks up the light into different colors. And it's not only just colors. Remember, you also have the entire electromagnetic spectrum, so it could break it up versus gamma, versus X-ray, microwave, radio. It can do all those things, yes? Now, a normal telescope that we find on Earth is going to be using visible light, okay? So you would have spectroscopy with just like those visible color light waves, okay? So the last thing is time monitoring. That's number 3. And we can focus on one star and we can look at it for a long period of time, okay? And look at like this one. This is the brightness of a star. This one period is 331 days, yeah? So that in 331 days, we're seeing that it was changing its brightness up and down over those 331 days. So we can tell about how variable a star is. If it's getting brighter and dimmer and brighter and dimmer. And with this, we can actually determine when it might die, when it might go supernova, things like this, when we might see some very cool events in the night sky. Okay, and last slide here is if you want to get your own telescope. Okay, first thing you would want to do is you would probably want to just buy some good binoculars. With good binoculars, you could use them, and you can see the Saturns of the rings around Saturn. You can see the moons around Jupiter. You can see a lot of things that you would normally see with a telescope. But if you do want to get a telescope, they always throw this thing called magnification on it. They'll be like, oh, this has 250 magnification. You made 250 times bigger. That doesn't matter, okay? It's a sales gimmick. And you need to know this. I asked this on the homework. It's a sales gimmick because, like, let's say you got a really, really bad image on like, I don't know, it's like an 8-bit picture, okay? And you blow it up to 250 times the size. It's just 250 times as not visible. Like, it's not good. It's not a good image. It's not going to help you define anything. You're not going to see anything better. What you need are those two important things of the telescope, which we said were light collecting area, so the size of it, and the angular resolution, which also has to do with the size of it. Okay, so really, telescopes, the bigger you get them, the better, okay? There's not really you don't want to look at magnification. You don't want to look at any of that stuff. There are some things here that you would want to look at, okay, instead of just looking at size, because quality is also a good part of it and making the picture more crisp. But the size is going to be the big thing, okay? So that is everything for 6.2.